change how we use continuous actions.
All right. Thank you, everyone, for coming in bright and early. So this is, I thought about what to discuss for this because diffusion is one of these things that we use in RL and robotics, but it's not like it's not something that we think about very, very deeply. So this is not like a kind of a grand vision talk with some kind of like unifying theory. It's really more kind of an overview of a few examples of settings where it seems like, for reasons that are mysterious to me, diffusion makes a big difference. So take this more as sort of multiple case studies of what exists rather than some kind of grand conclusion. The grand conclusion is sort of up to you to draw based on what you can figure out. And I just sort of want to tell you about my experiences. Okay, so this is going to be about continuous control and how diffusion models have made a significant impact in reinforcement learning and in robotics. Here is a video from the Pi0 Robot Foundation model that's doing a pretty complicated task. This is actually a pretty old video. It's about 2 years old at this point, folding a pair of shorts. This is a model, this is a 4 billion parameter model that has a vision language backbone and then a DIT-style diffusion output for continuous actions. Okay, so, and since we've done this work, lots of other folks, and as well as ourselves, have developed all sorts of different continuous control systems for robots and all sorts of other things that can do pretty intricate, pretty dexterous stuff. So what's going on here? Well, we have a model. That model takes as input a bunch of images. In this case, it's 3 images, one from the base camera that is looking over the top of this, and one camera on each wrist, as well as continuous readings from the robot's joint encoder, so proprioception, that goes into a big neural network. And that big neural network outputs what is called an action chunk. An action chunk is a short sequence of actions. In this case, it's 50 time steps, about 1 second, that indicate the target positions for all of the joints, the target joint angles. So conventionally, we denote this as a conditional probability distribution, denoted with the letter pi, which is the first letter of the word policy, and it's a conditional distribution over actions, given states, or in this case, action chunks. So A here is actually a little trajectory of actions. Okay, so that's all pretty straightforward. And traditionally, when people started training these kinds of end-to-end continuous control systems, they chose some fairly simple distribution class, like a Gaussian distribution. So your big neural network would basically output the mean and the covariance of a Gaussian distribution. And that was considered to be a pretty reasonable idea because from a bit of a reinforcement learning theory, we know that if you have a fully observed system, then there should exist a deterministic policy that is optimal. So if you believe there exists a deterministic policy that is optimal, then a Gaussian is like a pretty reasonable thing to do because there's a mean, which is deterministic, and there's a little bit of noise around it, and you kind of want the noise to go to 0 anyway, so you don't care so much about the distribution class. But the reason that this really started to break down is that when we went from developing sort of RL algorithms for simple systems or imitation learning algorithms for simple systems to working with large amounts of real data, then it became really important not just to think about what the optimal policy is, but rather what is the best policy you can get from your data. So in imitation learning, this is of course fundamental because in imitation learning, you're not even trying to improve over the behaviors that you see in the data. And even in reinforcement learning these days, you would typically still use lots of prior data to bootstrap the process. So even if your system might have a deterministic optimal policy, you might not be able to discover it, and the distribution in the data really matters. There are some settings where it matters a great deal. Let's say that you are training a drone to fly around a tree. This is good, and this is good. But of course, averaging those two together is not good at all. So there are situations in the real world where you want to learn from data where averaging your modes together into a single Gaussian is terrible. And no amount of philosophizing about deterministic optimal policies is going to save you. So the principle behind using diffusion in control is very, very simple. Instead of outputting a Gaussian, you take this huge neural network and you make it a diffusion model. Not a diffusion model over images, but over actions. This is a very nice illustration of this from a paper by Chi et al., the diffusion policy paper. They're actually visualizing the denoising process for a little action chunk, and this hopefully gives you sort of an intuitive picture of what an action chunk looks like. Okay, so that's the principle. And then I'll tell you about a number of case studies to kind of show you different perspectives on this idea. Any questions at this point? Yes?
Some very basic questions about the last slide.
Yes.
So when you parameterize the Gaussian, then at every side you sample from this Gaussian, presumably?
That's right. Although in practice, people often just take the mean, and they just represent it as a Gaussian just so that you have a probabilistic model, basically.
And the density of the Gaussian is like important in the objective? Like somehow there's something in, like you have some objective that involves like a likelihood?
Well, yeah, so typically if you're doing imitation learning, you're going to be doing maximum likelihood learning. And if you're doing reinforcement learning, I'll talk about it later, but it's roughly the same thing.
Okay.
Yeah, so really the right way to think of that Gaussian is it's basically just a deterministic policy. You just need something in there so you can pull a probability out of it. Okay, all right, let's talk about kind of a little historical digression and the basics of where some of this stuff came from. So, as far as I know, this paper by my student Michael Janner, as well as Yulin, who's sitting there at the back of the room, was I think the first paper that did diffusion for control, although it's not by any means the most popular one. The most popular one is the one on the next slide. But it's kind of an interesting, I guess, historical footnote to illustrate the evolution of these ideas. So the idea in this paper was to propose a method called diffuser, which takes the notion of using diffusion for control very, very literally. It just says, hey, diffusion is a way to model a distribution over images. Well, let's just like replace the images with trajectories. That's it. So in the same way that you have image pixels, here you have a 2D matrix where every column is a different time step and every row is a different degree of freedom, and we're literally going to just run diffusion to generate trajectories. And if we do that, then we can, for example, do in-painting to like condition on the first time step and fill in the rest, pull out the first action, take that action and actually use this for control or planning or what have you. So it's kind of the most in some ways, the most direct way to apply regular unconditional diffusion to do control, planning, and imitation learning. There was like a little bit of fanciness to have the model be represented with a temporal convolution so that it could be factorized a little bit, but basically it's just unconditional diffusion over trajectories. This is an illustration from an experiment that actually Yulin ran on doing some manipulation with this, where there's some constraints that are enforced with guidance to get this robot arm to stack some blocks. Okay. But the model is just an unconditional diffusion model over trajectories. And to control, you basically can do stuff like in-painting, for example. So you know that with diffusion models, if part of the observation is known, then you just fix that and fill in the rest. And then if you want to enforce constraints, objectives, rewards, etc., then you do that through guidance. Okay. That's a fairly natural way to apply kind of classical diffusion ideas to control. This is not the method that ended up being the most popular for control. The most popular method is actually a lot simpler, and it came about a year later by Chi et al., called diffusion policy. And that's the video that I showed before. And here, this is actually the diagram from the paper, but I think it makes this seem more complicated than it really is. The beauty of this method is that it is much simpler and easier to use than the trajectory level unconditional diffusion. It's basically a conditional model over actions given observations. The reason this picture looks complicated is because they have both a convnet-based way of doing this and a transformer-based way of doing it. These days, everybody would just do the transformer version. And all it is a conditional diffusion model over action chunks. The input consists of observations and, of course, the previous noisy step of diffusion, and that's basically it. And it's called diffusion policy, so whenever you name a paper, use like a very catchy name that describes exactly what it is, and it'll be much easier for people to remember. So a lot of the modern work on using diffusion for control basically derives from this work. Okay, now what does this look like today for modern policies? These are two examples of more recent works that use diffusion for control in some way, and they basically have the same ideas in common. And the ideas are not at all surprising to anybody that's familiar with modern diffusion architectures. So you use DIT-style transformer blocks, and then you have some kind of input, your observation, and you have to condition on that input somehow, and you do that with either cross-attention, or if you want to use like a transfusion-style architecture, full self-attention. But the distinction between those is actually kind of thin, so if you want like a rough mental model, think about it as DIT block with cross-attention into an input encoder. That like roughly gives you the right idea of how all this works. And very important detail, always output an action chunk, so not just one action, but a short sequence of actions. So this kind of picture, nobody really knows why that's so important. You would think that a policy that updates the action every single time step would be just fine, but somehow, at least in imitation learning, and increasingly also in reinforcement learning, outputting an action chunk works much better. And what I would say there is that for imitation learning, it's basically essential, like it just doesn't work without it. For reinforcement learning, it's not essential, but tends to make things better if you do it right. Okay, so that's kind of the present state of things. Any questions about this? Yeah.
Is the whole action chunk implemented, or only the first action implemented and then repeated?
Yeah. So the question was, is only the first action in the action chunk implemented and then you recompute the whole thing, or do you play back the whole thing in open loop? So the answer is you play back a portion of it. If you play back just the first step, then it doesn't work. Like that is one of the first things people think of. Oh, is it just a training time benefit? It's not a training time benefit. You do have to actually play back multiple actions. You don't have to play back all of them. So for that shorts folding example in the beginning, it's a 50-step action chunk of which 25 steps are played in open loop. Yes?
So is this trained with an RL algorithm?
So far, everything I've talked about is actually imitation learning. I'm going to talk about RL later in the talk. Yeah, but good question. All right, so now I'm going to take a little bit of a digression and discuss a different branch of robotic learning research, specifically robotic foundation models, that at first will seem a little disconnected from all of this, but then I'll connect it up to these diffusion policies and explain how they actually fit together really well. So first, a digression. Robotic foundation models. What's the idea? Well, the idea is that if you want general purpose robots that can do lots of stuff, you would like them to be able to understand diverse instructions and carry out lots of tasks. And if you want to do that successfully, then you need to train them on lots of data. And you also want to make sure to pre-train them on data from the web that allows them to understand images and language. So there are a variety of ways to do it, but roughly speaking, the recipe is get lots and lots of robot data, typically from many, many different tasks, and use some kind of pre-trained model, like a vision language model, that already understands the relationships between images and language, or videos and language, and then fine-tune it to control robots using your robot data. And this has been a very active area of research. Lots of companies, lots of academic labs have been developing all sorts of models. And it's been pretty successful. Like, it's possible to get models trained on large data sets that can do lots of pretty fancy stuff. Okay, what is some of the motivation behind folks working on this topic now? One motivation is this idea that a more general model can outperform more specialized models, even in domains where those specialized models are specialized to. So an experiment that kind of illustrated this point early on was the RTX project. The idea here was to go to lots of different academic labs and ask them to essentially donate their robot data to science. So there were 34 research labs in total. And they contributed data from 22 different kinds of robots. And there's lots of statistics I could show you, but it's maybe easiest to take it in from just the videos. So these are actual snapshots from the data set. You can see lots of different robots in many different domains, lots of camera viewpoints, all that kind of stuff. There's a commonality here. They're all single-arm manipulators with a parallel jaw gripper. So that's a pretty significant restriction to the embodiment class, but otherwise lots of variability. And then, so this experiment was led by Google. It was actually led by my colleague, Quan Vuong, who took all of this data and he trained one of these robotic foundation models on all of it. And he sent it back to 7 of the labs that participated and asked them to test it in comparison to the best model that they had developed on their particular domain. So each lab had a different model because, of course, back then, this was sort of, it's like the Tower of Babel story, like nobody's actually working together, everyone's doing their own thing. So we asked, okay, whatever you're doing, just compare our model to your thing. The average success rate, and averages over such a heterogeneous set are kind of weird, but by whatever metric each lab had, we just averaged their metrics, which is not the greatest statistical exercise, but you got to do something. 41% average success rate. The generalist model, 63%. And this is particularly wild if you consider that Quan, who trained this model, he didn't visit any of these labs. He didn't know that much about each of their tasks. All he did is took all of their data, put it together, and trained the model. So the fact that the first attempt at this essentially yielded a 50% improvement in success rate kind of suggests that there's something real here. Like, this isn't a case where somebody sat down and really overfitted the experiment to that particular domain. So what does it say? This says that the generalist model, the one that is trained on many different settings, actually outperforms the specialists on the domain that they're specialized to in all sorts of really weird tasks. Okay, so this got people pretty excited about robotic foundation models. And lots of folks started working on this. The first recipe for robotic foundation models was pretty naive. So it was basically inspired by how people built vision language models. To build vision language models, you start with a language model. It does next token prediction. That's pretty straightforward. So if you want to also do perception, you take an image, you embed it using some kind of vision encoder, followed by an embedding layer into the same token embedding space as you use for your language tokens. You have to be a little careful on how you train this thing. You have to train the adapter and then train the whole thing together. But basically, you get a model that can perceive images through like roughly the same embedding spaces it uses to understand language. So then people said, like, hey, well, this is already a model that takes in images. Let's just get it to output robot actions. And initially, the way people did it is literally by just replacing the suffix for these language examples with a language representation of the action. In fact, the first version that Yevgen Chebatar trained at Google literally used ASCII representations of numbers as the action, which is about as kind of ridiculous as it sounds, but it worked. And it actually led to significant improvements in generalization. So this is the diagram from the original RT2 paper. There's a bunch of VQA examples, the kind of things you'd use to train VLMs. And then the robot examples are kind of put alongside those. Basically, each robot example is like a visual question, where the question is the command, like pick up this object, and the answer is a sequence of numbers representing the action. Here are some videos of what this looks like. And the thing about these results is that back then, this was, in robotics world, kind of an impressive step forward in language following capability. But in retrospect, the tasks are like pretty rudimentary. And that's actually not an accident. It's not like we decided that we wanted to have particular simplistic tasks to more cleanly illustrate the language following. It was because these tasks were indeed the best we could do. So why is that? Well, to use a slightly egregious metaphor, the vision language model augments a language model with like a little visual cortex, if you will. Like the job of this image encoder is to take in complicated, messy image pixels and put them into a representation that is more amenable to this language model brain, if you will, to parse. Because images are complicated. Well, actions are kind of complicated too. And if you want to handle complicated actions in the same way as complicated images, maybe you need a little motor cortex, if you will. And because this model doesn't have one, then its motor skills are rudimentary, even though its language and image understanding capabilities are quite good. So what I would kind of fancifully call second generation VLAs basically augmented this design with some kind of separate neural module that was responsible for producing really good actions, not just actions represented by a sequence of ASCII numbers, but continuous action chunks that are high dimensional, high frequency, and much more dexterous. And of course, the way to do this was to use diffusion or flow matching. This is the architecture from the Pi0 paper, but there are many other architectures that use more or less a similar type of design. This is a mixture of transformers design. Other folks also use a separate diffusion head, but it's the same principle that you have some kind of DIT-based mechanism for producing continuous action chunks, and it can somehow attend to representations inside of the vision language model backbone. So second generation VLAs add a dedicated continuous output mechanism. And here's one of the results from this model, actually. This is doing the laundry, so it controls all the degrees of freedom of this robot, including the base, drives over to the dryer, pulls out all the laundry items, goes to the table, and folds all the clothing items. This is about 2 years old at this point, and this model is running end-to-end for this entire task. It's not perfect. It does make some mistakes sometimes. It takes a little while to fold some of the items, but basically works. OK, here are a few more results just to kind of keep everybody entertained. There are a few things that I wanted to point out here that are kind of interesting. We spent a bit of time messing around with the system, so you can see here in these videos on the right, Michael, who is the researcher running this experiment, perturbs the robot by putting some extra items on the table or messing up the items as it's folding. And this policy is actually pretty good at recovering from these things. And kind of anecdotally, like something that I've observed pretty consistently is that diffusion-based policies do tend to be pretty good at recovering from mistakes and kind of stabilizing in ways that doesn't always happen with, let's say, discretized or tokenized models. So that's pretty nice. Just to kind of bring this back to the present so that we're not only looking at things that are 2 years old, this is a more modern version. This is the Pi 07 model, which is essentially the latest version of this kind of design. based on very similar principles, now with much more sophisticated language following, annotations, and prompting. So in the same way that video models went from very rudimentary commands to being able to parse very complex commands, this one can parse more complex instructions, including instructions about how fast the behavior should be and how many mistakes it should make and stuff like that. And then it does all sorts of other behaviors. But the core design is actually very similar. It still has that diffusion block with a mixture of transformers architecture to allow it to use a vision language model backbone. See, not perfect, lots of mistakes, but then it recovers from the mistakes. Okay. I should say that over the last few years, there's been quite a lot of work on vision language action models of various types, as well as their cousins like video action models and so on. Models that basically combine some kind of web scale pre-training with action generation using a dedicated, let's call it, neural motor cortex, if you will. And they all roughly share the same anatomy, that there's some kind of component that's trained on web scale data and an additional circuit that does the action generation. Yes? So typically, they're trained end-to-end, but there's actually, the next slide touches on exactly this. So naively, what everybody would do is they would train the vision language backbone on web-scale data, then they would attach the diffusion component, and then they would train the whole thing end-to-end. That would be the standard way to adapt this for robotic control. Now, it turns out that there's a little bit of a problem with this, which we found about a year ago. And we developed a little solution. The solution is not very elegant, and I think that there's room for a better solution. But basically, the problem that we found is that if we trained end-to-end with diffusion, we would get a good result, but it would take a very long time to train. If we train end-to-end with discretized actions, those like ASCII number representations, it wouldn't be as good at the end, but it would train much, much faster, 5 to 10 times faster. And it kind of makes sense because your objective for training a diffusion model or a flow matching model is going to be higher variance, and it's going to take longer to converge. It was a little surprising to us just how much longer. 5 to 10x is nothing to sneeze at when you're burning, hundreds or thousands of hours of, high-end GPUs. But it makes sense logically. The other problem we found, and this was actually a little more surprising, is that you would actually lose a lot of language following capability. So the original Pi0 model, which fine-tuned end-to-end, basically we were finding that this action expert, when it's trained with diffusion with the gradients propagating back into the vision language model backbone, was kind of scrambling the backbone. It was making it actually worse at language following after fine-tuning was done. So we developed this thing that we kind of fancifully call knowledge installation. It's a fancy way of denoting something very, very simple. Basically, put a stop gradient between the action expert, the diffusion model, and the rest of the VLM backbone. That's kind of a natural thing that essentially freezes your backbone. That's not good enough because your backbone does need to adapt. You need to pay attention to the kind of visual features that matter for your robot task and the kind of language that matters. So instead of freezing it entirely, you add a second loss with discretized actions. So it's kind of a weird hybrid architecture where the discretized actions are used to provide a representational learning loss to the rest of the backbone, while the diffusion model is trained with a stop gradient so it doesn't affect the representations. And this actually ended up working a lot better, even though it's kind of a weird hybrid thing that seems like it might be the worst of both worlds. So let me explain this plot. I apologize, the resolution on the monitor is a little bit low, but basically the yellow curve, this is basically the learning curve. Y-axis is average task completion. These are real-world robot evals. The yellow curve is this method with knowledge installation. This line, the one that's doing pretty badly, is pure end-to-end fine-tuning with diffusion. And the gray curve here that's right alongside it, this is basically discretized actions. And this is an easy task. So this is the task that can be solved with just discretized actions. It doesn't require diffusion. And you can see that this knowledge installation method is equally fast. And then if we look at harder tasks, here the discretized actions are quite a bit worse than the diffusion-based method. This is pure end-to-end diffusion. This is pure discretization. This is joint training with discrete and continuous actions, but without the stop gradient. And this is with the stop gradient. So this is the full method. So you can see that actually on the harder tasks, there's a big gain in final performance, and on the easier task, there's a big gain in speed matching the training speed of the discretized method. And this is, I believe, about a 5x improvement in training speed over end-to-end training with diffusion. Now, my read on this is not that this is necessarily a great idea. My read on this is that there is a problem. Like the fact that you can, the fact that you actually get a better diffusion model by not fine-tuning the backbone with gradients from your diffusion model, that seems not good. And perhaps there is a lot that can be done to improve the training efficiency of these methods without requiring this kind of kludge to make it work. Yeah, any questions about this?
The discretized actions come from the backbone itself and not the action head?
That's right. Yeah, so basically the way the sequence is structured is you have like images, prompt, discretized actions with a loss. There's an attention mask so that the diffusion backbone doesn't get to look at them, and then you have diffusion. Yes?
May I ask why do you care so much about training speed? Is it because it's like done online, or?
Well, I care about training speed here because I'm paying for it. But yeah, these models take like weeks to train on hundreds of GPUs. If you crank this up, this was a 4 billion parameter model. You crank this up to like 32 billion, and now you're burning a very significant budget just to train each of these things. But maybe the more scientifically deep reason is that training speed kind of, you can think of it as trading off against model performance. So you can say, okay, I have a fixed budget, I'm going to train for a week, and training speed basically determines how good I am, right? So if you're only training for a week, if your model trains faster, you essentially get a better model. And in practice, the way scaling laws work is if you're getting more learnings per flop, so to speak, you're going to get a better model at the end as you pour in more data and more parameters.
I have a question.
Yeah.
Do you freeze all the weights?
So nothing is actually frozen. There's just a stop gradient between what's called the action expert here, which is basically the mixture element that does diffusion, and the rest of the backbone. Okay. I think I have still some time left, so I'm going to talk about reinforcement learning. This is a different chapter of the story with also kind of perhaps a surprising conclusion. I think this might be interesting to you guys. I do need to put in some background here because reinforcement learning brings in quite a lot of additional machinery, but there is also an interesting conclusion about how diffusion made a difference in reinforcement learning. So first, a quick primer. Many of you might already know this, but what is RL? In RL, you have an agent that takes actions. They're denoted with A. The world responds with states S. And you have rewards. So instead of just matching the data, your goal now is to maximize the expected total reward. So you'd like to take actions that will lead to high rewards. And one of the things that's very important these days, especially if you're doing robotics, but also in many other domains, is to be able to do this kind of reinforcement learning, but leverage offline data. So classically, reinforcement learning is an online process where your agent continuously interacts with the world, collects more experience, and so on. But in reality, you would really like to bootstrap this process with lots of good data. So maybe take that policy that can fold the shorts, use that to start reinforcement learning, and then train it from there to become even better. And that's basically a kind of offline to online process. So you start with an offline reinforcement learning recipe where somebody else collected data using some policy you don't know. You ruminate on that data to get the best policy you can, and then you go out into the world and improve it further. And this makes a lot more sense if you're in a domain like robotics where you really don't want to start from scratch. You don't want to start from the robot just wiggling the arms randomly. You want to start from the best you've got and then make it even better. And this is kind of the dream. Now, achieving this requires two things. It requires being able to do this offline phase effectively, basically pre-train your reinforcement learning system, and it requires doing the online fine-tuning effectively, basically take whatever you got here and actually improve it. And both of those are a little difficult. The offline phase, roughly speaking, what you want it to do is not just be a better version of imitation learning where you just copy the data, but you'd like it to take data that's kind of heterogeneous and pull out the best possible thing from that heterogeneous data. So if you've seen, for example, lots of human drivers driving cars in different ways, you'd like to get a policy that is like as good as the best human driver in each situation. And that's roughly what offline RL is trying to do. Okay, I won't go into this in too much detail. A quick primer about how we actually do this. So a very important object for this is called a Q function. A Q function is a function of a state and an action that tells you if you start in this state and then take this action and then follow your policy pi, what is the total reward you will get. And if you can train a Q function for your policy, one of the things you could do is you could immediately get a policy that is as good or better by just taking the argmax of the Q function. And this is the basis of something called policy iteration. So you basically alternate between learning your Q function and then picking a new policy that just takes the argmax and then repeat this process. You can also short circuit this process and write out a recursive expression for the optimal Q function. This is the Bellman optimality equation. And if you can find a function Q star that is equal to the reward plus the max over the Q value at the next time step, then you can show that the corresponding greedy policy is in fact the optimal policy. And this is basically the basis for Q learning. So a very standard way to do this would be to say, like, hey, let's start with this Bellman optimality equation, take the difference between the left-hand side and right-hand side, and minimize that difference at all our states and actions. If we can do this successfully, then we'll recover the optimal Q function, and from that, the optimal policy. And people really like this idea because when you set up this minimization, nothing here is actually assuming that the states and actions that you're minimizing this on came from any particular policy. So this is a really great foundation for any kind of off policy or offline RL method, because you can just set up this minimization on all of your data, use that to train your Q function, and go out and get more online data. At least that's the principle. And in practice, like, this is kind of the last bit of good news here. After this, everything starts getting pretty rough. And the problem we start running into is distributional shift. Because unlike with imitation learning, where we're just trying to copy what we saw in the data, now we're actually trying to change the behavior. And when you change the behavior, now you're basically trying to evaluate a policy that is different than the one that collected your data using this old data. There's a few ways to write that Bellman optimality equation. I'm going to write it like this, which makes the distributional shift problem a little more obvious. So the standard Q learning method is to pick the maximum over the next Q function, but that's the same as taking the expectation of that Q function under some new distribution, in this case, the distribution that assigns a probability of 1 to the argmax. I know it's kind of weird to write a max as an expected value, but a max is an expected value under the deterministic argmax distribution. Okay. And now this expected value will be accurate as long as the distribution under which Q is trained is similar to pi. Right? That's kind of the obvious learning theory result. But of course, that's not the case because you train the Q function under your distribution in the data, which is not the same. Like, the whole point is you want pi to be better than the distribution that collected your data. So this doesn't actually work. You have catastrophic distributional shift. And even worse, you're picking your policy based on your Q function. So it's like optimizing for an adversarial example. It's like optimize for actions that will fool your Q function into thinking that you have a large value. So naively, this is very, very bad, and it basically doesn't work. So most of the research in this area for the last maybe 6-7 years has focused on finding a good way of addressing this problem without unintended consequences. I'll tell you about one way of doing this. This is not necessarily the best way. This is a fairly old method, but it's quite easy to understand, in my opinion, because it's, if the problem is adversarial examples, the solution is basically adversarial training. So there's this principle called pessimism that says if you don't know the Q value of some unknown action, just assume that it's bad. And one way to implement this, very similar to adversarial training, is to basically take your Q function, your Q learning objective, which is minimizing the left-hand side minus the right-hand side of the Bellman equation, and add a kind of adversarial regularizer that says, let's find these adversarial actions using an adversarial policy pi and minimize their value. There's a second term that says also maximize the value of the actions in the data set. That's kind of funny, but it actually makes sense if you think about it, because you're minimizing the value of the actions from this adversarial policy. And if the adversarial policy is the same as the data, then this term and this term cancels out. So this second term is there so you don't get too pessimistic. Essentially, whatever action you're trying to take, make that bad. Whatever actions in the data, make that good. And if you're trying to take actions that are similar in the data, then these two terms basically cancel out and you don't bias yourself too much. If you want to think of this visually, let's say that green curve is your true function that you're trying to fit. The blue curve is your fit. Pretty good everywhere, but you go to the max, and that's the one that is the most erroneous. So we find those maxes and we push them down. That's basically the idea. Okay. So there are other ways to correct this issue, but they all kind of have some flavor of this, where they're trying to deal with this distributional shift. And these things basically work. Like you can prove stuff about them. You can apply them to all sorts of domains like dialogue systems and digital marketing and so on. So these things provide you with a way to train on offline data. So far, so good. But remember, the motivation was to train on offline data and then improve using online interaction. And that's where this thing really, really breaks down, as well as many other offline RL methods. So when we started playing around with this, we thought, okay, we've got like an offline RL method that's pretty good. Let's do some online RL fine-tuning. This is the reward versus training time in the offline phase is getting pretty good. It's saturating. So clearly here, this is a good time to start some online exploration because you've squeezed out all you can from the offline data. Let's go. And this is what you get. So you actually spend a significant chunk of the online phase degrading performance and then crawling all the way back up. And this degradation is really bad because, of course, by this point, you've more or less forgotten what you're doing. That's good, and you have to kind of relearn it. And then, of course, if you train long enough, online RL does work and you get there. But it seems like you're losing most of the benefit of that offline training. And this is very consistent. Like on many, many problems, and with a variety of offline RL methods, you will see some kind of degradation like this. So this is bad. Like if this was an autonomous vehicle, for example, we train on a bunch of offline data, the first thing it learns to do when we put it on the road with online RL is it learns to crash, and then gradually decreases the number of crashes, hopefully, until you've before you've exhausted your fleet of autonomous vehicles. So this is bad. Why does it happen? Well, there's actually a formal explanation, but I'll do my best to give like a short, informal explanation. If you think about what these pessimistic methods are going to be learning, they're going to learn some value function that like close to the data is hopefully pretty good, and then far from the data, they're not going to overestimate too much. Okay? So this is kind of a reasonable cartoon for what's going on. But then when you start exploring, of course, where are you going to go? You're going to go here. You're going to go to the new places. Because if you don't go to the new places, then what's the point? And this is where you have large error. So you go to these areas with large error. The fact that you're training pessimistically is actually increasing this error because it's saying let's underestimate more so that your offline phase doesn't go there. You go here, you get hit with large gradients, scramble your function, and end up with this dip. So when you start collecting online data, these points are no longer out of distribution. You're actually training on them, so you do actually want to get them right, but they're way off from their true values, and you get pretty bad results. There's a more rigorous treatment of that problem in this paper, but that's roughly the intuition. So in fact, there's like an embarrassingly strong baseline that for a very long time would outperform all the fancy offline to online RL methods, RLPD, which basically just says like, hey, if you have prior data, don't even do offline pre-training. Just start running online RL, but load, for every batch that you're training on in online RL, load half the batch from your offline data. But don't bother with pre-training at all. And this was kind of shockingly good for a long time, and it's kind of sad because it means that you're just like not allowed to pre-train properly. I'll skip the robot results for this because I want to get to the answer. Okay, so here is the answer. And it involves diffusion for reasons that I don't fully understand, but I'll just tell you about it. So there is a different class of offline RL methods that are, instead of being based on pessimism, are based on constraints. So instead of changing something about the Q function, let's change something about the objective for this new policy. Instead of picking it to maximize your Q value, pick it to maximize your Q value subject to a constraint that you're not too far from your data distribution. And it makes sense why this would help, because if you're not too far from the data distribution, then this expected value will not be too far off from what you're training the Q function to do, because you're training it under pi beta, you're testing it under pi, so if pi and pi beta are close, you should be okay. Now, people had this idea a long, long time ago. It just never worked that well because everybody was using simple Gaussian policies. So if your data distribution is really complicated and your policy is really simple, you have an unenviable choice. Either average your modes together, in which case you're putting some weight on very low probability regions, and then you do get distributional shift, or pick one of the modes, in which case you're essentially just throwing out a lot of your data. And neither of those are good. So people concluded, myself included, some time ago that these policy constraint methods, maybe they're just not that great, and we should do something else. But of course, the surprising key idea is that if you have a very powerful policy class that doesn't have to average the modes like this, then this thing actually works, and it actually works really well. If you use, and again, this is kind of the paradox for RL, because RL researchers naturally would have said like, hey, it's an MDP, there exists an optimal policy that is deterministic, I don't need fancy policy classes, but it turns out that if you have a fancy policy class, you can use this kind of policy constraint method, and that ends up not having this pessimism problem and working quite a bit better in offline to online mode. Now there's still a problem because you have to train your actor to maximize Q values rather than to fit your data, so diffusion models don't make it easy to do this, and we need to get kind of clever with developing a method that can train a diffusion model to maximize value. These days there's lots of methods for doing that, but it was a journey to get there. But once you can do this, then you can use this constraint in offline mode, and then you can run online RL with that same constraint if you want to limit deviation, or you can relax the constraint, and all of these problems with pessimism don't arise, and things end up working pretty well. I wanted to tell you about some methods for doing this, but I want to be conscious of time, so I'll tell you about one method, not this one. I'll tell you about the simplest method, okay, which is diffusion steering. So there are multiple ways of using diffusion for offline to online RL, but this one happens to be very simple, and it actually works quite well. So here's the idea. Start by training your diffusion policy with offline data using imitation learning. So basically all the stuff from the previous section, no RL whatsoever. Take your data, imitation learning, diffusion, and what do you get? You get a neural network that basically knows how to map Gaussian noise to reasonable actions. Not optimal actions, but just reasonable actions that are in distribution. And in particular, every sample of Gaussian noise maps to an in-distribution action. Now this gives us a really nice way to solve distributional shift. Instead of doing control in this space, just do control in this space. So now RL isn't actually going to train the diffusion model. RL is going to train another network that looks at the state and outputs the noise, which goes into the diffusion model. And that actually ends up working really well. And in fact, you can use a naive online RL method in both offline and online mode because there is no more out-of-distribution action. So that problem with the adversarial examples doesn't exist here. And that's exactly what this method does. It uses a standard naive soft actor critic method, which is a purely online method, in the noise space. And then that can be used to adapt online. It can be used to train offline. This is a real robot experiment where this robot learns in about 50 trials how to put the mushroom on the cloth. Sorry, it's an academic experiment. It's not as fancy as the cloth folding, but it's pretty fast. And this is an offline RL experiment, purely an offline RL benchmark where it's matching the state of the art. And that's pretty nice because now you have a method that matches both state-of-the-art offline RL results and runs in online mode and doesn't have to do anything fancy except for using this imitation learned diffusion model. And these are pretty hard benchmarks. Like these are complicated long horizon tasks, solving puzzles, navigating mazes, stuff like that. Yes?
I don't quite get why this fixes the problem. If you're off the support to the Gaussian, would it not be possible that you generate?
Well, it's very easy to keep you in the support of the Gaussian because you know what the shape of the Gaussian is. So you just impose action bounds on this thing and just say, like, don't go outside of the unit ball or something like that. Because the trouble with this thing is that you don't even know where the support is. Yes?
For the long horizon puzzle task, is the Q value just the score of the game?
So on that task, the reward is 1 if you finish the puzzle and 0 otherwise. So the Q value ends up being you apply a discount, so it's roughly an exponential transform of the number of steps until you complete the game. Okay. There's other methods I could talk about, but in the interest of time, I'll skip over this. And there's just one thing I wanted to mention for conclusion. Takeaways. So diffusion-based policies in RL solve an important problem, which is offline to online learning. Kind of a surprising answer out of left field, but it seems to work. You have to take a little bit of care to adapt them to train actors in RL. That requires some care. There's a section I skipped. You can actually use guidance for some of the policy extraction stuff. This is a method called CFG-RL. You can read about it if you're curious. There's other ways of doing it as well. But I want to conclude by telling you a little bit about how all these things can be put together. So these days, I think one of the most exciting areas for robotic foundation models is actually to combine some of these imitation learning ideas with RL and do that at scale. We've been working on this a little bit at Physical Intelligence in the last few years. One of the methods we developed, PyStar 06, basically combines these vision language action models with value functions. The values are actually added to the prompt of the VLA. So you basically condition it on some language and also like, hey, this is the value of this action. And then at test time, you can condition it on high value and it'll produce good actions. And you can do an online training phase. So as I mentioned, these methods are good for offline to online, and that's really convenient. Without going too much into the architecture, I wanted to show you some results. These are some of the, time-lapse trials we did. So when we trained these things with RL, they became more robust and more reliable. So we thought, well, we have this coffee-making task. Let's see how long we can run it for. We ran it for 13 hours in the office. Everyone came away very caffeinated and worked really hard for the next 24 hours. It failed occasionally in those 13 hours, but it knows how to clean up the coffee machine when it fails, so that's pretty good. And this is in a chocolate factory, Dandelion Chocolate. The robot is working to assemble these boxes. So it folds the box, puts a sticker on it, puts it on the crate, and then Dandelion can go and put chocolates in this thing. So the policy is using diffusion to generate action chunks, and there's an RL component that gets it to improve with experience, and it actually is running at scale. There's some quantitative results here. The important curves to pay attention to, the green bar is basically the best offline result. The yellow bar is from then adding the online RL phase. The y-axis here is throughput, so number of successful task completions per hour. And you can see that there is a pretty significant increase from green to yellow across all of these tasks. And you can put these things together. You can actually train one model on all of the different tasks, including the RL data and the advantage conditioning, and get a pretty nice generalist policy. So as we go to questions, I'll leave you with a video of this thing doing some pretty cool tasks with diffusion to generate actions and with RL to optimize them. Yeah, any questions?
So I mean, Sinho touched on this already, but like when you go from Gaussian, then everything is in distribution. But maybe the limitation is that, like in some sense, you can only cover the support of the pre-trained model, right? Like because it's mapped through the. I wonder, like, I mean, KL as like generically, if you're regularizing with KL, right? It's generically either like mode seeking or mode covering, like regardless of like how expressive your policy is. I wonder if you've experimented with like other kind of distributional metrics like Wasserstein, which more like maybe satisfyingly split the difference?
Yeah, so there is a kind of there's a neat method from Perry Dong in Chelsea Finn's group at Stanford that actually does something like this, where I'm trying to remember this. I think what he does is he has a separate residual policy, meaning that it's essentially a model that outputs a little delta to the action from the diffusion model. And now, I don't know if he actually has this in the paper, but it's kind of an obvious conclusion that that would be a Wasserstein metric, because if you bound how large the residual is, then you can move away from the support by a bounded amount. Yes?
So you make this analogy that like offline is more like pre-training and then online is like fine-tuning afterwards. Is there also an analog of like reasoning phase?
That's a good question. So one analogy, and this is something that people actually do quite a lot, and it works very well, is to combine the diffusion models with RL using a best event strategy. So generate multiple sampled actions from the policy. The policy can be an imitation learning policy. Evaluate the Q value of each one, and then play the best one. And that is actually a very effective strategy. You can combine it with some of the other policy extraction methods. So you can, for example, do diffusion steering to bias towards good actions, but then still sample multiple and take the best out of those. And that actually seems to pretty consistently help. So I guess you can think of that as an analog to test time compute. Not exactly reasoning, but test time compute. Yes?
I had another quick question about error accumulation. So you mentioned that these policies are relatively robust to correcting errors. But like when I talk to my empirical friends, like when they train conditional diffusion models on like video prediction, like just like next frame prediction, they seem to like always observe these like error accumulations where like the color will drift or these kind of errors. Like what do you think prevents that?
I think there's a difference in expectations here. So my expectation from having worked on control is that error accumulation is like really, really bad, and I'm like pleasantly surprised by how it's like better than I expected. Whereas I think for the video folks, maybe their expectations that there won't be too much of it and they're disappointed when it happens. So I wouldn't say that error accumulation goes away by any means. It's just less bad than I would have thought it would be.
Great, so let's have the next speaker. Our next speaker is Yilan Du from Harvard University, talking to us about compositional reasoning with diffusion models.